So this is the first in probably a series of videos of project showcases where I'll be going over some of my projects and talking about them. I wanted to make these videos because especially for the projects that aren't on the web, that aren't just websites that you can easily access, a lot of my projects are kind of difficult to access and run just in general because to open these programs you'd have to download these files from GitHub or like clone the project, clone the repository, and then compile it and run it, which is kind of a hassle and I wouldn't expect most people to do it. So in these videos I can show off the projects and you can still get a sense of the features and how they work and what they do without having to go through that process. But I'll do it probably even for the web projects because I can also talk about the design choices and the motivation behind them and show off maybe some cool little details that I really am especially interested in. So the first thing obviously is that you can pause and play the simulation and you can see, of course, it's pretty self-explanatory. It simulates pendulums. So we can see the simple single pendulums. They're all simple pendulums, which means that the mass is entirely concentrated in these points, right? So it's just point masses. These arms don't have any mass. The single pendulums have this very predictable motion. We can click this button to turn off the traces to see the weights more clearly. The single pendulums have a very predictable back and forth motion, just completely periodic. It's just like sinusoidal, right? But while the double pendulums are a little more chaotic, they sort of swing around. This one's kind of calmed down, but they can be pretty crazy, and they're pretty chaotic. We can clear these default pendulums and create one of our own. So the first thing that I'll show you is that the scale of the pendulums is 1 pixel is 1 centimeter. So that means 1 meter is 100 pixels, right? So this 1 meter pendulum is 100 pixels long. And that means you could actually calculate, whoops, that's the wrong field. You could calculate the period of the pendulum using, right, the period of a pendulum is 2 pi square root of L, the length of the pendulum, over the gravitational constant G, which I'm using Earth's, which is 9.8 or 9.81 around there. And it would come out to be almost exactly the same, right? Because we're using some numeric integration, which I'll show off kind of the math and design of that later in the source code. But that numeric integration has some small error that builds up over time, especially. And so the period is ever so slightly off by, a hundredth, a tenth of a second. I haven't measured it, I'm not sure. But for the most part, you could see, it's mostly accurate, right? So you could see, for example, the effect of the length of the pendulum. Let's add a shorter one on the period, right? The shorter one will have a much shorter period, right? It'll swing faster. Because the longer one has to swing this long distance. We can even add maybe a really short one will go kind of crazy. Yeah, it's almost vibrating. You can't even see the arm. You can also see that the mass, so this mass field, obviously we weren't filling it out before because the mass literally doesn't affect things for a single pendulum, right? The mass cancels out. It's kind of the same reason. It's analogous to why an object in free fall, they all fall at the same acceleration, right? So an object with more mass has more weight pulling it down, like the force of gravity, its weight is stronger, but because it has more mass, it also has more inertia, which means it's harder to move. So that those effects kind of cancel out. The force of gravity is pulling on it with more strength, but it's harder to move, and those effects kind of cancel out. So they have the same acceleration in free fall. This, of course, is not free fall, so it's a different situation, but it's kind of the same relationship, basically, right? That the period doesn't, or the behavior doesn't depend on the mass at all, right? Because gravity's pulling on it with more force, but the higher mass means more inertia. And so this looks like a single pendulum, but I added, remember, different masses. So they're all following the exact same behavior. If we add some double pendulums now, things get more interesting, right? So we could add like 120. I like to add more extreme angles because then they have a little bit more energy, so it's more interesting to look at. So these angles are from the vertical, And you have to add the masses because the masses do affect things for a double pendulum. Okay, that's too long. Hold on. So if we add equal masses, just looks pretty normal. You can kind of, we'll see how the mass affects things in a second. These pendulums swing around, and it's kind of more erratic motion, right? And the trace is also more interesting to look at for a double pendulum, for the outer pendulum, or at the outer weight, because it kind of actually forms an interesting pattern instead of just arcing back and forth in a circle for a single pendulum or for the inner weight of a double pendulum. It follows this sort of interesting snaking pattern. It's pretty, it can be kind of mesmerizing, honestly. But if we add of different weights now, let's add like 10. So this is the inner pendulum, and this is the outer. So this one, in this one, this 10 is going to be on the inside, and we'll see that that outer weight, because it has less mass than the inner one just kind of overpowers it, and so the outer weight just kind of swings around pretty wildly. So that's pretty fun to look at, actually, doing these crazy loop-to-loops. And if we do the opposite, if we do the inner weight is more, then that means it'll just kind of overpower, or sorry, the outer weight is more mass, then the inner one will be kind of overpowered. And it almost looks like a single pendulum because the outer one is just kind of becoming the dominant factor, right? The inner part is just like sort of bending to its will, I guess, colloquially. It's just being overpowered completely. Okay, it looks like it's actually, okay. I thought it might be gaining energy for a second. So we can also see the chaotic nature of motion. So let's say of double pendulums, they have kind of chaotic motion. So we'll do equal masses, and then we can just alter the starting angles ever so slightly. So we'll do 119. I'll actually leave it vertical anyways. Whoops, I did not mean to pause. So I'll just change the inner angle, so 120. So that's just changing the inner arm's angle. The vertical, this second arm is still just going to be straight up because of the 180. So I'll change 120. So we have three pendulums, 119, 120, and 121. And you'll see that pretty quickly they deviate completely, and they don't really follow similar paths, right? So that's chaotic motion. Given slightly different starting states, they deviate kind of completely from each other, and it's really difficult to predict how they're going to deviate. So that's pretty interesting, right? You can watch them swing around for a little. So that's pretty much all the features of the actual project itself. But I am going to talk about some of the math and design and physics behind it. So the first thing is that I'll show you the formulas, right? So for a double pendulum, these really long formulas are, I didn't derive them myself because unfortunately I don't really understand. I believe they're derived with Lagrangians, right? This is the Wikipedia page for double pendulums. Because they're so complicated, it would be difficult to do them, maybe impossible, I don't know, with Newtonian mechanics. And I don't really know Lagrangian mechanics. I haven't taken like a mechanics class. But so these formulas are pretty much what I'm using directly in my code. So this is omega 1 prime. So that's the angular velocity, but the derivative of the angular velocity. So that's angular acceleration is equal to this state. So there's an explicit formula for the angular acceleration, but we don't have an explicit formula for the actual angle or even the angular velocity. So to get those, we can numerically integrate, right? Right, like it just says here, numerical solution, which basically means there's different methods to do that, but where am I looking? Yeah, so as it says here, no closed form solutions. So the solution can be solved numerically. So the simplest method of doing that is the Euler method, basically. If from Calc 1, hopefully you remember. Or if you don't know, basically it's pretty simple. So you have a formula for the derivative, like you can know the slope, and you have an initial value, but you don't have a closed form, then you can use the Euler method to approximate the closed form. Why is this page not scrolling right? What's wrong with Chrome? Maybe I have too many tabs open. So you basically have your original value, yn, and then you take a small step h and multiply that by your derivative, f. Like f is the function that's giving you your slope, and that gives you your new value of y. And you can see here, so the red curve is the original function, and this purple or blue curve, Wikipedia calls it blue. I don't think it looks blue. Oh, there. Oh, I think the colors are off because I'm in dark mode or something. This blue curve, it takes these discrete sort of steps. It's piecewise, right? Taking a step along the tangent of the red curve, which we have a formula for. And you can see the error builds up pretty quickly. But if you had smaller step size, it would build up less quickly. The green is some other method entirely, so that's not. It's like a midpoint method. But with a smaller step size, you'd be more accurate. For double pendulums, right? Or sorry, for the fact that we're doing it for acceleration, right? That we have an explicit formula for the acceleration, angular acceleration, means that we have to do this step essentially twice. We have to do this Euler method to get the speed, and then we have to also do it to get the position, right? So this is essentially the Euler method, right? Just we're doing it twice. So you take the acceleration, which is like your f in this situation, and then divide it by the frame rate, right? 1 over the frame rate is essentially our step size. Like each frame time, each new frame, that time between frames, is a little step in time. And then the plus equals is essentially taking the old value and adding it to that value. This, yn plus that to yn plus 1, it's the same thing as plus equals. So we do that to get the speed, and then we do that to get the angle. The interesting thing about this is that little detail, the order of these operations, matters a lot. If we change the order, that really affects things. So so that's something called the semi-implicit Euler method, or the Euler-Kromer method, where specifically, if you do this, if you calculate the new speed first, and then use that Vn plus 1 in the formula for your x to calculate your new x, or position, that affects things. That's the difference. That's the key difference. So that says it right here. The difference between the standard Euler method is that the semi-implicit Euler method, which is what we're using, uses the Vn plus 1, the new speed, or in this case, angular speed, angular velocity, in the equation for xn plus 1, which is the new theta. In our case, we're using theta, they're using x, same thing. While the Euler method uses Vn, the old speed. So if we just change the order, now we're using the old speed. So this is the Euler method. And as this little article from the University of Delaware says, as Kromer pointed out, that modification of using the new speed, Vn plus 1, conserves energy for oscillatory problems. So a pendulum is oscillatory, right? It oscillates, like, it's periodic. It goes back and forth like a sine wave. And if we rerun this using this rearranged, so this is the default Euler method now using the old speed, then pretty quickly you can see that the energy of this double pendulum and also the single pendulums will start to just increase, right? The single pendulum is swinging around itself. It started from just a normal angle. It shouldn't be swinging completely around, but it is. And if you watch the outside, these longer single pendulums, they start swinging higher and higher, and eventually they'll start swinging like this inner single pendulum. They'll start swinging just completely in a circle as well, right? Because the energy is building up, which is completely inaccurate, right? It breaks the laws of physics, so it's a really inaccurate simulation. Because the energy should remain constant, right? This simulation is supposed to be without friction, without damping, so the pendulums never slow down and stop. They should just remain constant energy, but this is just increasing out of nowhere. And also, the traces kind of show you, give you an idea of the speed that these pendulums, even if you pause it, you can see that these pendulums are clearly moving pretty fast because of those traces. Right. So that's pretty much everything I have to say about the design, or at least the actual physics. The other practical lesson I learned from making this project is that SFML is pretty, or just in general, graphics libraries they're kind of bare bones. SFML, which is Simple and Fast Multimedia Library, it's pretty bare bones. Unlike, develop when you're doing web development, if you have HTML and CSS, or even in the past I've done projects in Java using Java effects, a pretty nice uh, GUI library. Uh, they give you kind of a lot of features, right? So they let you define like layouts and buttons and all these different UI elements. Not so in SFML. And I'm sure if you were using OpenGL, it would even be even more bare bones, right? So you have to define everything yourself. They pretty much just give you shapes, geometry. So you could draw a rectangle, and they give you input events like a mouse event, but you have to kind of make those components yourself, right? So I had to make a button myself and say like if a mouse event is in the bounds of a button object, do some function on click, and you have to define changing the cursor yourself and changing the color of the hover and the layouts, the arrangements of all these UI elements. You have to manually explicitly define them in pixels. You don't get a flex box or a grid layout like in web dev. So it was kind of a hassle, but it's interesting and it makes you appreciate the tools you have when you do have them to just define a simple layout. So that's everything about the design itself. But the last thing I'll say is that if I ever continue work, if I have the time to maybe add a feature, is the next feature I'd probably add, which would be a significant change, would be the Runge-Kutta method for integration, for numerical integration, because it's more accurate, right? It uses yn plus 1, this new value, is equal to yn, the original, but instead of just adding like a single slope times a step, you kind of averaging together these slopes, k1, k2, k3, k4. That's one type of Runge-Kutta. Apparently it's a family of methods, and it uses these different slopes and sort of averages them together to be more accurate. And so some of the inaccuracies of our simulation would probably be helped by using that Runge-Kutta method. Because I didn't show it, but unfortunately, if you have pendulums of, let's do it on a guideline. These guidelines are 30 degrees apart, by the way, 30, 60, 90. If you have them at different angles, theoretically the angle of the pendulum should not affect its period, but in our simulation it does. It doesn't, it's pretty close, so you don't see it immediately. But that difference in period, that slight difference in period, which is kind of inaccurate, will build up over time, and clearly you'll see that they clearly have different periods, which is, they should be swinging all in sync. And I believe that's because of the numeric integration method, that it's introducing some error, right? Like that picture of the Euler method, there's going to be some error from the actual true value. But the Runge-Kutta method is much more accurate. You can actually see up here on this example function, the second and fourth order Runge-Kuttas follow the original function, this red curve, pretty closely, whereas the Euler method is building up a lot of error pretty quickly. And even if you're using an Euler method with a smaller step length, half the step length of the Runge-Kutta, so that's like an advantage for it, it still has a lot more error, even with that advantage. So yeah, clearly these pendulums are a little inaccurate. Especially they build up that error over time. So if you let it run for a while, it'll be pretty inaccurate. At least in exact timing. Overall, though, it's fairly accurate. But yeah, I had a lot of fun making this project, learning a little bit about some of these physics formulas. Oh, I was able to derive, of course, the single pendulum myself, because that's simpler. It's just negative g sine theta over L. Let's see if I can find that. Whatever. That's the formula, just trust me. And it was interesting to learn about some of the physics, some of the differential equations a little bit. Even though I don't really understand Lagrangian mechanics now, I did read a little bit about them and get a little bit of exposure to them. So that was interesting. And I think it's a pretty interesting project to look at. It can be a double pendulum, can be kind of mesmerizing to look at sometimes. Creates these cool patterns. So that's it. Okay, a little addendum to that video. I realized that after I recorded it, the comment I made about the error in this, specifically in the situation where the pendulums of all the same length but different initial angles don't have the same period. I thought that was due to the numeric integration method that, building up error over time, but actually it's because of an intentional design choice, and actually it was kind of more accurate, right? The way I did it, because so when I talked about the period of a pendulum not being dependent on the initial angle, right, where I said t equals 2 pi square root of L over G, actually that formula depends on the small angle approximation. So that only holds true for small angles, right? So essentially the small angle approximation is when you're deriving these formulas, if you do, so this is the second derivative of theta with respect to time, so that's angular acceleration equals, it's exactly equal to negative g over L sine theta. So that's what I originally had, right? That's what this was before. And that's what I showed at the end of the video. And I said, just trust me. But using approximation, most of the time, to have nicer formulas, we use a small angle approximation, which is saying that sine theta for small angles is approximately equal to theta. And that makes things a lot easier and a lot easier. It gives you easier equations to work with, right? And that's a good approximation for small thetas. But for big thetas, which we often use in these projects, right, or in this program, right, you could have a theta that's 90 degrees or even above 90 degrees. You could have a theta that's 179 and it swings almost all the way around. So in that situation with big thetas, that approximation is really bad, and we can actually show off, right, just using Desmos. This sine curve, it's obviously sine, and we have the line x. And you can see for small angles, right, so these are in radians instead of degrees. We've been talking degrees, but it's the same idea. The line is very close to the sine curve for small angles. But as you start to get farther away, that up to 90 degrees or pi over 2, that approximation is way off. So actually, the original use of the formula negative g over L sine theta results in more accurate simulation. It's just people don't normally use it in physics because it's just worse. It's annoying. It gives you kind of difficult to work with equations. But since we want an accurate simulation of large angles, that's what I was using. But if we rerun the program with using the small angle formula, right, using negative g theta divided by L, which is equivalent, which is what's used for this period calculation, and we play, then the pendulums will actually be perfectly synchronized. So it's not the error in the numeric integration. But actually, this is more inaccurate to the real world, because 60 degrees, this line, is actually would make the small angle approximation not a great approximation. So I'm going to stick with my old version with the sine theta. That's it.